Now today in class 12th, I am taking the topic torque on a bar magnet placed in magnetic field. We know that the bar magnet contains the north and south pole, so that acts like a magnetic dipole. So when this dipole is placed in the magnetic field, then there is a torque acting on this magnet. Let this is the magnetic field. Magnetic field B. This is the uniform magnetic field. This is a bar magnet. This is bar magnet. Let this is S pole and this is N pole. Let 2L equal to effective length of bar magnet. Now the force acts on these poles. This is F equal to mb, and here the force acts like this, F equal to mb. On both the poles, magnetic force acts, and on the north pole, this is along the direction of the applied magnetic field, and on the south pole, this is opposite to the magnetic field. Here we have you can have the idea that this north pole is just like the positive charge and south pole is just like the negative charge. So the two forces are acting on the poles. So let M equal to strength of magnetic pole. Each pole is of the same strength, so force on each magnetic pole, force on each magnetic pole, this F equal to mb. Now these forces are equal and opposite, so net force on the magnet is 0. Net force on the magnet, this is equal to 0. But these forces constitute a couple. Because of that, the magnet starts to rotate. Now this force has the tendency to rotate it along the direction of the magnetic field, while this force has the tendency to rotate this dipole opposite to the magnetic field. So these two forces have the rotating or the turning effect. The forces on the magnetic pole have the tendency have the tendency to rotate the magnet. So it forms the torque. It forms the torque. Now this torque, as we know, by definition, this is equal to force into perpendicular distance of line of action of the force. So now let we make a right angle triangle like this. This is the axis of the magnet and it makes an angle theta with the direction of the magnetic field. So this is equal to, let this now point your P. So this is now force F into the perpendicular distance between these two forces is NP. So this is equal to F into NP. Now since this length is equal to 2L, so this is your NS sin theta. Sin theta equal to this perpendicular to hypotenuse. So this F equal to MB F equal to MB into NS, this is now your 12 sin theta. So now here triangle SPN sin theta is equal to your NP upon NS. So this NP equal to NS sin theta. So this is now your 2L sin theta. 2L sin theta. So now we are having this 2L sin theta. So this is M into B sin theta. This is now torque. Where M equal to M into 2L, magnetic dipole moment. Magnetic dipole moment. So in vector form, this torque is equal to M cross B like this. This is the cross product of the magnetic moment and the magnetic field. So torque equal to cross product of magnetic moment and magnetic field intensity. This B is called magnetic field intensity. So now some special cases. Special cases. Now first, if theta equal to 0 degree or 180 degree, it means the magnet is parallel to the magnetic field or anti-parallel to the magnetic field. So what we have parallel and anti-parallel? That we have the direction of the magnetic moment. The direction of magnetic moment is from south to north. So now suppose here this is the B and this is the magnet. This is S and this is N. Then the M will be in this direction. S to N. So we have this magnetic moment M is parallel to B. Then torque equal to MB sin 0 and sin 0 equal to 0, so torque equal to 0. It means that no torque acts on the magnet when it is parallel to the magnetic field. This is the most stable condition of the magnet. It is most stable condition of magnet. Now second, if theta equal to 90 degree or pi by 2 radian. In this what we have? Let this is the magnetic field B and the magnet is placed in this way. This is S, this is N, then magnetic moment will be in this direction M. So now they are mutually perpendicular. Then what we have? Then torque equal to MB sin 90 degree and sin 90 is equal to 1, so this torque equal to so much. So torque equal to 0, this is the minimum value, and this is the maximum value, torque equal to MB. It means that when the magnet is perpendicular to the magnetic field, then torque is maximum. It means that the magnet will have the larger tendency to come parallel to the magnetic field. So from here you can also define the magnetic moment in terms of the torque. Definition of M, the magnetic moment. Now we have this if theta equal to 90 degree and B equal to 1 Tesla, then torque equal to M. It means what? That when the magnetic moment of a bar magnet is equal to the torque when it is placed at right angle to the uniform magnetic field of intensity 1 Tesla. the magnetic dipole moment is equal to torque when the bar magnet is placed perpendicular to magnetic field magnetic field of is placed perpendicular to magnetic field of intensity 1 Tesla. Magnetic field of intensity 1 Tesla. This is the definition of magnetic moment. One more we know from right from the beginning of the chapter. This is now one from this magnetic in terms of the torque. So you can see that torque is maximum when the magnet is perpendicular to the magnetic field, and this is minimum or zero when this is placed parallel or anti-parallel to the magnetic field. So this is about the torque on the magnet. So thank you very much.